You know the periodic table. We've all seen it hanging on a classroom wall, right? Just a bunch of boxes and letters. But what if I told you it's not a chart at all? It's a treasure map. It's a cosmic code that, once you know the rules, unlocks the secrets of pretty much everything in the universe. So today, we're going to crack that code.
So let's get right into it. Is this thing just a list of elements to memorize, or is it more like a puzzle box where every single piece, every element, has a specific place for a reason? Well, it's totally the puzzle box. There are hidden rules that dictate its entire structure, and once you see them, you'll see the patterns everywhere.
You know, way back when, chemists were basically sci-fi detectives. Seriously, imagine someone hands you a bunch of cards, and on each card is a different alien. And you have to sort them by their features. You know, how many eyes they have, maybe how long their arms are, so you can figure out what a missing alien in the set must look like. That's exactly what early scientists were doing with the elements, just looking for that hidden order.
Okay, so here's our game plan. First, we'll look at how to crack the code itself. Then, we'll dig into the size of an atom, which is key. We'll see what happens when they change size, explore the whole energy game with their electrons, and then we'll put it all together and see the big picture. All right, part 1, cracking the code. We're going to get right to the heart of it and uncover the fundamental forces that make all these patterns happen in the first place. And really, the very first key we need is all about
The size of the atom, or what chemists call the atomic radius. And I'm not kidding. If you can wrap your head around this one single property, everything else just kind of clicks into place. It really is the master key to the whole map.
So, what is atomic radius? It's basically just how big an atom is. Simple as that. We measure from the very center, the nucleus, all the way out to its fuzzy edge where the last electrons are hanging out. And the unit we use is picometers, which are ridiculously tiny. We're talking a trillionth of a meter.
Now, to get why atoms are the sizes they are, you need to know about this one force, the effective nuclear charge. Honestly, the easiest way to think about it is like an atom's own personal gravity. You've got the positive nucleus pulling on the negative electrons, and that's what holds the entire thing together. The stronger that pull, the more compact the atom is.
So this leads to the two major trends that define the whole table. First, as you go down a column, atoms get bigger. This makes sense, right? You're adding whole new layers of electrons, new shells. It's like putting on another coat in the winter. You just get bigger. But now, here's the weird part. As you go across a row from left to right, the atoms actually get smaller. How? Well, you're adding more positive protons to the nucleus, which cranks up that gravity we just talked about, and it pulls all the electron shells in just a little bit tighter.
Okay, so what happens next? Well, atoms aren't just sitting there. They can gain or lose electrons, and when they do, they become something called an ion, and their size can change a lot. This is a story of ions.
So let's look at sodium. A normal sodium atom has this one lonely electron in its outermost shell, and it's not very attached to it. When it loses that electron, it becomes a positive ion, which we call a cation, and it shrinks. Why? Well, think about it. You have the exact same nucleus, the same positive charge, but now it's pulling on fewer electrons. So its grip on each of the remaining electrons gets way stronger, and it yanks them all in closer.
And this isn't a small change. A regular old sodium atom is about 190 picometers across, but the sodium ion, it shrinks down to just 95 picometers. It literally becomes half the size, all from losing just one tiny electron.
Now let's flip it. Let's look at chlorine. Chlorine is the opposite. It loves to grab an extra electron. When it snags one, it becomes a negative ion, an anion. And what do you think happens? It gets bigger. This time, that same nucleus has to hold on to more electrons, so its pull is spread a little thinner. On top of that, electrons are all negative, so they repel each other, pushing that outer shell even further out.
And just look at this transformation. A neutral chlorine atom is 79 picometers, but the chloride ion, it blows up to 181 picometers. It more than doubles in size. This constant battle, this push and pull between the nucleus and the electrons, is pretty much what drives all of chemistry.
So that brings us to the economics of the whole thing. It costs energy to pull an electron away from an atom. And on the flip side, atoms often release energy when they gain one. It's this sort of energy economy that's happening all the time.
Have you ever done this? Accidentally put a fork or a piece of foil in the microwave and zap, you get that crazy light show of sparks? What you're actually seeing there is the microwave's energy physically stripping electrons right off of the metal atoms. It's a perfect real-world picture of what we're about to talk about, ionization energy.
So ionization energy is basically the price you have to pay, in energy, to remove one electron from an atom. Now, following our trends, as you go down a group, that price gets cheaper because the electrons are further away and easier to grab. But as you go across a period, the price goes way up. Those atoms are smaller, the nucleus has a death grip on its electrons, and it costs a ton of energy to steal one.
And you can really see it in the numbers. Let's just look at period 2. Over on the far left, you've got lithium. It's pretty cheap, only 520 kilojoules to pop off an electron. But then look all the way over on the right at neon. Whoa, it takes over 2,000. That's because neon's outer shell is perfectly full. It's stable, it's happy, and it does not want you messing with its electrons.
Here is a perfect way to picture this. Just imagine electrons are like paper clips, and the nucleus is a really strong magnet, okay? The energy it takes for you to physically pull a paperclip off that magnet, that's ionization energy. Now, what happens when you bring another paperclip close to the magnet? It just jumps on with that satisfying snap. That little snap of energy being released, that's electron affinity.
So, electron affinity is the energy change, and yeah, usually it's a release of energy. When an atom gains an electron, it's like the reward it gets for accepting a new one. And guess what? The trends for this pretty much mirror ionization energy. The atoms over on the right side of the table, like our friend chlorine, have a super high electron affinity. They really want that extra electron, and they give off a lot of energy when they finally get it.
Okay, we've looked at all the individual rules, the size, the ions, the energy. Now it's time to zoom out and see how it all fits together to create this complete, beautiful map of the elements.
And this chart really says it all. As you go down, atoms get bigger, and because they're bigger, it's easier to take their electrons. As you go across, atoms get smaller, which makes it harder to take an electron, but the reward for gaining one gets a whole lot bigger. See? It's all connected. One property directly affects the others.
So here's the absolute biggest takeaway. All of this, all these complex sounding trends and properties, they all boil down to just two really simple ideas. First, the strength of the pull from the nucleus, and second, how far away the electrons are from that nucleus. That's it. That's the whole secret. That's the code.
And just like that, you've cracked the code. For real. Now you can look at that table and you just know things. You want to find the biggest atoms, the ones that give up electrons easily? Look to the bottom left. Want to find the smallest, stingiest atoms that hold on for dear life? Top right. It's that simple. And that leaves us with a final thought. Right now, scientists are trying to create a brand new element, element 119. So based on everything you now know, where would it sit on the table? And what could you predict about it? Would it be a big atom or a small one? And would it be easy to take an electron from it or really hard? You've got the map now. The answer's right there.